All right, so this is lecture 10, exactly halfway for the quarter. And this is the last class on hydraulics. Today we are going to learn about open channel flow, which is most of the time the case when stormwater move from one area to another. So one of the important characteristic of storm flow is that you have to measure the flow rate. And you learn how they are done in the real world, at least in many cases. So that's the class today. And on the we have some announcement. First is again office hour every week, Wednesday 1 p.m. We met some students this week. We discussed about homework. We also discussed about the project if you have any question. So do attend the office hour when you can. But if you have class on Wednesday at 1 p.m., you can always meet me any other time if you send me email, or you can meet the TA. TA is there to help you any question you ask. Mostly he's there to help you for your project. But homework question, as I said, we discuss in the class, so you should not have issue with homework. You should ask another students because we discuss every question here. Homework 3 is due this Friday. Homework 4 is out today, so it's due next Friday. That's the last homework for this quarter. So keep working on homework and finish it on time. So all these homeworks is part of the the midterm questions. And I also shared the last year example midterms for you to start preparing for your midterms. And midterm this year is on May 13th, which is Thursday. Um, but one important aspect of midterm is it's 24 hours. That means it will be released on Thursday and it's due on Friday. So that means you have entire time to work on the midterms. By the way, I don't expect this to take longer, even though I give you a whole day to work on it. This is just so that because this is a project-oriented course, so I just expect you to work on, it's open book, close colleague. So that means you can't ask or you should not ask any other person to help you on midterms. It's open book. It's 24 hours. So the moment it released, anyways, D1, it's released on Thursday the 13th. I don't know, let's see if it's 13th or not. Yes, Thursday 13th, and it's due is on Friday. And usually you have 24 hours. Any time you can start working. It's not like a timed, so it doesn't really matter. And you write on your own page, whichever page you want, and scan it and send it to us. Upload on Gradescope. And from now on, also in the second, we have already started doing this one from last class. We'll have second half for entirely discussions to do example problems as well as real world project brainstorming, so that you have some knowledge about the projects that you are going to work either as part of the class or when you graduate, if you work on green infrastructures. So during the second half, we can pick any project. Either I pick any random projects, which is nothing to do with this class, or you can decide that this is your team projects can be part of the discussion. So as a whole class, we can discuss, brainstorm, share ideas. This will help all of you. So we're going to transition to class discussion from next, because we, as far as the material is concerned, after next week, everything is kind of applications. Next week is the last week for any kind of numerical examples or problems. Today, again, as I said, we are going to learn about discharge rate or flow rate. How do you measure flow rate for stormwater using Manning equations? This is the famous equations that everybody use. So you learn how to use it. Mostly you understand this conceptually. And you will also measure flow rate for pipe or weir based on the shape and size. All right, so one thing I want to suggest is that anything we learned today in this class, you'll refer to the handouts which is already shared on the course web page. So I'm sharing the slide right now. You can see this is what I see on my end for CCLE. So week 5 hydraulics. If you open this handout, everything we cover today or even last class, you have these materials here. So again, you can remember this is one of the example we solved last class. That's already here. So you can read it more if you don't have good understanding of what we cover. But at least this is the handouts you can refer to based on what we are going to learn today. So you'll see this kind of image, or even you see this image in the on the slide. So these are all from here. So you have at least um, some handout to read from if you don't have a good if you want to go back and read it. In fact, this is what we learned last class. So this is the questions, and if you could not understand, you can go back and check. It does explain everything. And there are other things in the handout over here. You can see this is also annotated one. And in annotated one, everything you can see in addition to if we discuss anything during homework discussion, it's already here. Okay, so you can see if you have difficulty. At least some of the question we already solved. This is one of the discussion we had for a project. One student asked questions, so you can see those. All right, so that's all for the handouts so that you can see where things are. Um, let's go back to the right. So the very first thing you do that before even we design green infrastructure, even in the part of the green infrastructure, you will have pipes to either direct water from some location to green infrastructures or to move water away from the green infrastructures. And some other places where you will have pipes, storm drainage. So those pipes are important part of the stormwater network. It's very important to understand how much head loss it occurs during the when water flows from one into another, because your goal of every green infrastructure is to reduce the flow rate as well as reduce the speed of water. So hydraulics is all about speed of water, how fast it's moving, how much volume is moving. So head loss because of friction is one of the way that you can slow down. Um, and that's what you'll learn a little bit today in the first next 10-15 minutes. So one of the things you have to understand is the flow rate, the head loss or the loss because of friction depends on the flow rate or the type of flow. So there are roughly we can decide two type of flow. One is steady flow, another is unsteady. Steady flow means the time the flow rate is constant all the places, or the velocity is constant everywhere. Unsteady flow means the velocity of flow rate is changing. Then there is also another kind of flow. Even whether steady or unsteady, there is the speed itself will determine whether it's a laminar flow or a turbulent flow. Turbulent flow is the picture that you saw here. Basically, it's mixed. The velocity is so high that things are moving not in a streamline. It's mixing up as it moves. So that's turbulent flow. That's just one example here. Before this one, this is another example where things are moving so fast that the friction loss is very low at the edge. But typically the velocity low, the laminar flow occurs. What it means is that the water molecule at the center, it moves much faster than the water molecule at the edge. The reason is this water molecule has a lot of friction. So this is there is a friction associated with when water collide or the move on the side of the pipes. So that friction loss is what's the cause of head loss. Okay, so that's there is a formula that you can use to calculate head loss. So first is how do you know whether it's a laminar flow or turbulent flow? Turbulent flow means there are a lot more frictions. So that's for that there is a dimensionless constant that we use, Reynolds number. That's basically the ratio of inertial force to viscous force. Inertial force is because of the velocity it moves, and friction, viscous force is basically the frictions. So because of those two, whenever the friction is much higher, then it's a laminar flow. That means if moving slowly enough, that friction makes a big difference in the velocity. Whereas inertial force is basically the movement, the energy of the water. So if it's moving very fast, it's basically inertial force is much higher. So that means the Reynolds number, if it is very high, in fact, the boundary is around 2300. If RE equal to 2300 or above, that means it's a turbulent flow. So when the RE is lower than 2300 or lower, usually it's a laminar flow. Okay. This is just one boundary. Below 2300, in some cases there may be turbulent flow at the local region, so you have to check. But roughly 2300 is the boundary. So this is again, as you see, if you want to calculate Reynolds number for any locations, this is the way you can calculate. So that's basically diameter of the pipes times velocity divided by kinematic viscosity. So viscosity again is related to frictions or the viscous force, and inertial force is all about velocity. Okay, and this diameter is the pipe. This is very important. The reason is if you have larger pipe, that means you have less. The Reynolds number is going to increase, or the another way to say is the inertial force will be higher, and you have to think of what's the reason behind it. If you let's have example, if you have a larger pipe, let's say this is d is 10, and let's say d is equal to, let's say this is no, maybe it's 5, half of it. So what that means is if the pipe becomes smaller and smaller, or let's say larger and larger, because Reynolds number increase with diameter, it becomes bigger and bigger, you have most water moving at the center, and very small fraction of the water is touching the pipe. But if you make the pipe smaller and smaller, a larger portion of water molecules are actually touching the pipe. So that means the frictional force is much higher. So that's the whole idea. Reynolds number is all about more inertial force. So and less friction force. So if the diameter decreases, you have more frictions because more fraction of water is touching what the pipe side or edge, and they experience that frictions. So that's why you can think conceptually what happens to Reynolds number if your size of the pipe increases. You can connect that conceptually. And one of the things that you have to think of is friction loss in pipe. So let's think of conceptually first how friction loss is related to these parameters. So think of this way. Now, what you learn, friction loss means when the water moves here, this is the velocity. I'm asking the friction that cause here because there is no friction beforehand. Also, friction can occur because water molecule itself is rubbing against another water molecules, but mostly it's because of pipe. So that's the side of the wall. So if I ask you velocity, if velocity increases, friction decreases or increases, because these are going to be quiz question in the next quiz. So let's think of conceptually. So friction, think of as a force, the opposing force, because moving another direction, you are going to experience other way. So think of another way of how to relate to this one. When you are driving a car, if you open the windows, you feel the wind, and so that's basically the frictions that you feel that wind when you move through the side. So now I'm asking this question: if you drive very fast, are you going to experience the speed much higher or the slower speed? So friction loss is going to increase with velocity or decrease. Let me,
Professor,
yeah.
wouldn't it change through laminar versus turbulent flow?
Yeah, that's true. But let's say the velocity, as it increase the velocity, whether the friction loss is going to increase or decrease.
Increase.
Increase is the same thing. If you drive faster, you will experience that force, right? So now friction loss will increase if velocity increases. Okay, and you know that friction loss is basically energy loss, right? Energy is related to, if you think of kinetic energy, half mv square, right? So that means the friction loss, the energy will be also proportional to velocity square. Okay, so that's proportional to velocity square because of that context. So this is proportionality constant, okay? Proportional. That's the way for me to write it. Okay. What about length? If you have a bigger pipe, is there going to be more friction or less friction? Any volunteers? Think of conceptually.
More friction.
Yes. So the friction occurs at the edge, right? So if you have longer pipe, there are more chance for water to touch the pipe. So that means this is also directly proportional to length. Okay, so that means if the length increases, friction will increase. What about diameters? This is diameter. If the more diameter, is this a friction decrease or increase relatively?
Reversely proportional.
Yes, inversely. We just discussed that. That means more fraction of water is going to touch, or less fraction of water is going to touch the pipe. More will be in the center. So that means we can say that inversely proportional to diameters. So that means if you increase the diameter, friction loss will, or if you decrease the diameter, friction loss will increase. If you increase the diameter, friction loss will decrease. What about roughness? That means a clean. This one should be easy. What happens to if the roughness increase? Is this going to increase the friction loss or decrease the loss? Or there will be more friction or less friction?
More friction?
More friction. Imagine water is going through a very plain pipe, it's not going to drop anything. If it is like edge has a lot of roughness, it's going to hit it. So that means there will be more frictions. So if the roughness increase, friction loss is basically proportional to frictions. So as you see, you have already kind of conceptually understand it. And now if you write the friction loss or the head loss, you already created that equation. So you said that increase in friction. So this is head loss because of roughness. This is length. This is velocity. And this is okay, and G is acceleration due to gravity. This is just the okay. So as you see, the way before we conceptually decide 1 over D, that's exactly the reason it's 1 over D over here. Okay. All right, so that means if you know this equation, you can calculate head loss by just putting this value. And that friction factor can depend on roughness and many other factors. But this is just F depends on materials. This is basically depends on roughness as well as pipe materials. Okay. Any question? So again, this will be one of the quiz questions. So at least you should know conceptually how it is. And you can read the handout. So if you have any other questions.
Professor?
Yeah.
I'm still a bit confused. So laminar flow and turbulent flow are both part of steady flow? or both part of unsteady flow?
So that's nothing to do with steady or unsteady. Okay, so steady flow means um, dq by dt equal to 0. That's steady. Okay, what that means is q is constant. Okay, that means if you collect water at different times in this pipe at any located time, you keep getting the same volume. Okay, so whether it's moving fast or slow, it doesn't matter. You are getting the same amount all the time. Okay, so that's a steady or unsteady. Whereas turbulent or laminar flow is nothing to do with the steady or unsteady. It's about whether it's moving at slow speed or high speed.
Okay, so basically they're just separate classifications. They don't really affect each other.
Yeah.
Like a laminar flow in the pipe could be steady or unsteady depending on the
Yes.
situation. Okay.
Yes. So basically, the velocity or the flow rate at one location is whether it's constant or not. Okay, that's the steady flow or steady state. All right, so now we learned the friction loss, which will be useful for you to design basically how big the pipe flow would be, what sizing of the pipe, so that it doesn't, you don't want the water to stay inside the system all the time. But really, it's not very useful for many of the design because it's not needed. A lot of times you can control it. The reason is you have, for instance, roughness. Stormwater pipe will accumulate a lot of sediment, so that will increase roughness all the time. And second, as you see, what's the design factor here is the diameters and length. You don't have much choices in terms of length. You just have to deliver stormwater from A to B. But you can increase the diameter so that it's less friction, so that stormwater move freely. But that's also cost. You have to dig more holes, bigger space, so that's something you have to consider. So those are pretty standard size. So you basically calculate this so that you know what's the friction loss. You're not really using this any other way. But measurement of discharge rate is something that you will do time to time in more cases. So if I ask you calculate the discharge rates in this pipe, what you do? You basically take a bucket or think of if I ask you to calculate what's the flow rate in your let's say when you open your bathtub, what's the flow rate? Um, the easiest way to calculate is if you have a 1 gallon milk bottle which is empty, and then you can take it and open the cut the top, so that you have more space, and you basically open the pipe altogether and have a stopwatch or your phone, put the gallon bottom and gallon bottles and see how long it takes to fill up, and you have the stopwatch. And so you take the time, you take the volume, this is the volume, and you calculate the time. Okay, and volume over time is flow rate. Okay, that's how you measure any pipe flow. You can measure volume flow rate by that. If it is something you can collect water. But in stormwater, in nature, you can collect all the stormwater. For instance, in this river or the stream, you are not going to collect all the volume of water at one point and measure it. That's why it's not easy to measure by just by volume way. There has to be indirect way for you to measure. So most of the cases they use certain techniques, and that's what we are going to learn now. So in open channel, you have this constraint. You cannot collect water, as I said. It should be easy enough for people to record it without getting into danger, because storm flow can be dangerous. If it's moving very fast, you don't want anything to go near. That's why it has to be safe. And also, by taking measurement, you should not block the water. It should move freely, right? So these are the criteria you have constraint for your to measure. And this is one example of how storm flow is measured. So that particular picture that you see over here, it's basically a wedge that you put into the pipe or into that channel, and based on how high the storm or the water level is, you can calculate the flow rate. So that's why most of this stormwater measurement is based on the channel and channel shape, how this is a, so this is what we call uh, Weir. So there are many different way, a different shape. This is a triangular one, the one you see over here. There could be rectangular, there could be trapezoidal, there could be parabolic, could be mix of all that. It has its own advantage, but basically by putting a known shape, you can estimate the flow rate based on the height of water itself. So we are going to learn that how it is done. Okay. So just to reiterate, the shape could be many things. It could be, let's say, rectangle, triangles, and trapezoidal, or mix of all. But this is like when you see this is the edge water is moving along with you. But if you see on the side way, these materials is basically a plate, like you see over here. It has a certain edge, so that width is here. No? So that's width, or the how it is designed is also going to affect the friction, or the friction loss. So that's why you can see there will be some, could be like a very much sharp, that plate is kind of very sharp at the edge, or it could be rectangular, or it could be circular, or it could be combination of all those. So those shapes are important in terms of calculating loss of because of frictions. And why these wires are used? They are used for flood control, or control discharge. Sometimes if you can lower this ways all the way to down, you can block the water some way, or you can release only certain amount of water based on the how far you can lower it. And those are for flood control, as well as maintaining certain amount of water all the time on the stream, which is important for ecology or fish. Um, this is also another way to, you can control invasive species, because if you put this one, any species from upstream, downstream will not come to the upstream. That way you can have a block or barrier. They can only move one directions. So as I said, the height itself will determine the flow rate. So this is one equation just for rectangular one and triangular one, which is very common. So the shape of the rectangular or triangular one is looks like here. So as you see, flow rate is a function of a constant discharge coefficient that's related to friction, like I said before. And then friction, or the edge, whether it's a, what kind of edge, whether it's a triangular or 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 rectangular, that C will be very different. So this function of this will affect that C. And then you have length as well as height of water. So as you see, length is basically this one, and that channel length, which is constant. You already know this one based on when you design or put it there. The only thing that can vary here is h. H is the height of water above that small locations. So that means this is the only, this is fixed, L is fixed, H is. So by just measuring height, which is very easy, you can put the scale, the marker, like this is up to here will be 1 inch, up to here 2 inch. So whatever is under the water, you can see that, and anybody can just record it by looking at that numbers. So then you can measure the flow rate just by measuring the height. And for the triangle, you don't need to have two dimension, because there are two other factors. One is the angle. Angle determines the length is replaced by angle times a height. Okay, so that's why this number changes. Basically, tan theta by 2 times h. So here, if you replace L equal to tan theta by 2 times, so this is L 3 by 2, 1.5. This is 5 by 2, so h, yeah. So if you replace, put this value over here, then this q equal to this value. Okay, and that's because, you know, if you see any triangle, let's say this is a triangle, and you are calculating what is the value of length. Length is this L. then basically you can calculate if you do theta here. So this L equal to, what is this value? This will be, if you say tan theta by 2 would be L divided by this height. L by 2 divided by this height. So that's how you can put L by L equal to tan theta by 2 times h. Okay, so you put that value over here. So that's how you can calculate. This is a converted into triangle formula. So bottom line, for this, you just have to know the equations and just plug the value and get the answers for your homework as well as quiz or midterms. Just understand conceptually how it comes from somewhere. So we'll have some example. For instance, this one example is find the discharge flow over a sharp crested wire as shown below. If the crest elevation is 282, I mean, it doesn't tell the units, but you can decide whether it's inch or feet. The impoundment elevation is 283. So these are all example in the handout itself. Okay. What we can do is let's do one thing. We'll solve this one in the discussion session. That way you can learn from it. But again, this is all about putting this equation and getting the answer. There is no difference here. As long as you know the height, you can calculate it. Same thing, find the discharge flowing over a 60-degree V notch. So that means this is theta, and the h is given. So you know h, you know theta, and your calculate is q. So basically everything is given. So same thing, other one is that. So it's pretty straightforward.
Professor,
Yeah.
is the impoundment elevation in that example the same as the head above crest, so variable
Yes.
h?
Yes.
Okay, thank you.
So basically, if it is a self-crested weir, so that means the water height h, or whatever that h, this is h here, h is 283.75 minus 282. So that means you know the h. Okay, so that's it. So then another question is, last time we discussed about orifice flow, where the answer was Q equal to some frictions times 2gh. Okay, so there is a difference between Weir flow versus orifice flow. Orifice flow means, it's completely, there is no space, there is no air when it's moving, whereas Weir flow is basically it's open channel, means there is a water head, water is one of the edge is basically water. Okay, so that's the only difference. So that you should know the differences. So in the previous, yeah, go ahead.
Professor, how do we find discharge coefficient again from the previous?
So those are given. The C would be given to you for different shape. Based on this shape, you can, those are given in the handout. You can just use that number.
Oh, okay. Thank you.
So this is given for shape of, okay. All right, so next is pipe flow. So pipe flow is most common in stormwater. Mostly is used circular pipe, really large pipe. Even though the pipe are large, doesn't mean that's always filled with water. It's always half filled or lower filled. Basically in LA, most of the pipe run dry. Okay, so that means it's become technically an open channel flow. So that means you have to calculate what's the flow rate. So flow rate in pipe, again, the same concept like we know before. It depends on the size or the length of the pipe, the velocity of the flow rate inversely. So there is a couple of things that flow rate will be affected by. Another thing that we don't account for in other places like here is the slope. because pipe, unlike where the pipe can be in an angle, and many pipes are on angle, because so that gravity itself can help water move. So that's why that slope is important. So there is another factor is slope, and the one thing that, as you know, the velocity depends on the friction will decrease the velocity. So that's why this is the roughness or friction factors. Okay, so friction loss. Then everything else is given. Okay, so again, there are two equation here. The reason is when you convert one formula to another, the units, then you have to put a constant here. If you don't write anything, no units, just SI unit, this is the equations. If you are English unit, feet for, or whatever that number, feet per second, then you have to use 1.49. So it's not the difference. Other than that, it's just a simple concept we already discussed. The only extra factor here that you didn't know is the slope. If you increase the slope, there will be more velocity or the more flow. That's because gravity itself will push. So again, use this equation to solve it. Any times that somebody asks, so this is, by the way, Manning equations. If you ever asked, what's the velocity of water in a pipe, you just use Manning equation, and that is this. Just know conceptually, we discussed that again. We don't need to discuss other factor. Now, question is the flow rate. If you have because I said the pipe always is not going to fill with water, how do you calculate the flow rate based on how far it is filled? So one of the things that you can decide the height, or you can decide other factors. So a lot of times, what people calculate is based on the weighted perimeter. Weighted perimeters means basically this is the entire perimeters, but if water height is up to here, that means only this much area is weighted. Okay, so this is weighted perimeter. So what it does it to calculate the flow rate, you assume that this is like a pipe, but what's the equivalent of pipe, assuming that all is entirely filled? So that's why effective radius of pipe is basically assuming it's an imaginary pipe if same water is moving, but it's completely full. So that's why effective radius is decided by weighted area divided by weighted perimeters. Because area by perimeter is, if you think of area of any circle is pi r square, and perimeter of any circle is completely filled, this is a 2 pi r, right? So if you divide this area over perimeters, you basically get r over 2. Okay, so that means this is directly proportional to radius. So that means this is the concept people use to calculate effective radius of a pipe if it is half filled. That means weighted perimeter. That's what is called A by P. So that means now let's decide how to calculate P versus area. Well, P is very easy to calculate. You just have to calculate what's the length of this one. You know that for entire angle 360, that's the area. That's the 2 pi r is the entire perimeter if the angle is 360. Okay. But if your angle is only theta, what the perimeter is P. So that's how people use. So basically they make a ratio to calculate this value. So perimeter is theta divided by 360 times 2 pi r. So this theta is in degree, not radian. So if based on how far it is filled, if somebody gave you theta, you can calculate weighted perimeter. That's all you are learning from these equations. And now if you want to calculate area, which is basically this is the area, okay, and this is the area of water, cross-section area of water. You can use these equations. I don't want to derive it. If you derive, then you will get this number. So basically this is the formula. Okay. If you get this number, this value, you can calculate the effective radius. Once you effective radius, you can calculate all this different flow and everything else. So let's have an example here. Find the quantity and velocity of flow in a 18-inch diameter concrete pipe flowing 1/4 full. The pipe has a slope of 1% and assume n equal to 0.15. So if you know the velocity, this is basically given to you. This is now in English unit, so let's write this one. So Q equal to Q equal to 1.49 times area divided by friction factors times and slope, I think 1.5. Okay. So this is everything is given. S0 is 1.0. N equal to 0.1015. That's the friction. So that means 1.5% of the fraction would be. Then the radius is given. Radius is 18-inch diameter, so that means the radius will be 18-inch divided by 2, so that's 9-inch. And slope is given, so this is given, n is given, area is also given. Area is the entire area of the area equal to pi. That's basically the effective. That's basically the the entire area. So it says find the quantity and velocity of flow in a unit diameter concrete flow if it is 1/4 flow. Okay. So now question is, it's not completely filled. If it is completely filled, you can use this one. If it's not completely filled, then you can have to calculate effective radius. Effective radius is this one. What is the effective radius for that? So how do you calculate effective radius? That one based on these answers here. A by P. And so if you know theta, you can calculate all of them. So that theta is given here, or it's not given. So that means you have to calculate that theta. So let's calculate that theta. So this one. So anybody, any suggestions? All you know is here is, you know the radius, which is 9-inch. So this is 9-inch. You got to calculate this theta. And you know this is 4.5-inch, this side. So that means you know this much is 4.5. If you know this much 4.5, this is total 9-inch. So that means this is also 4.5 because the total radius is 9-inch. So if you know this is 4.5, this is 9-inch, you can calculate also this side because, or if you know this too, you can calculate theta because theta is in this triangle. If I'm going to write this triangle like this is 4.5 and this is 9-inch. This is theta. So if you know cos theta is this side divided by the diagonal. So that will be 4.5 divided by 9-inch. So that means if you know the theta value, theta is, this is 4.5 divided by 9 will be 1/2. So that means 0.5. So you can calculate theta in this way. By the way, this will be radian, so you can change to degree. So if you know theta, then everything else, you plug this value over here, you can get that answer. Again, these are all drawn, or the example is from the handout. So if you don't understand it, go back to the handout and see the solution. So it's not really, I'm putting different example. So this is another 3 example. The only thing I changed is the height of the water. So that means the theta is going to change. So use these examples to solve it. That way you can calculate all of that. Any question?
So basically, we're just using one of the four formulas from 2 slides ago, and then the R from each of those four formulas is the effective radius if the water does not completely fill the pipe.
Yes, effective or hydraulic radius. If you see, this R is hydraulic radius. Which is what means now where the water is moving.
So hydraulic radius and effective radius is just the same term,
Yes.
right?
Yeah.
Different. Okay.
So the effective radius is always smaller than the pipe if it is not completely filled. If it is equal to, it's completely filled, then effective radius is equal to the radius of the pipe.
So, quick question for that example you just did.
Yeah.
Did you solve for theta or theta over 2?
You're right. You are right. This is theta over 2. You're right. Sorry.
Okay, perfect.
Cos theta over 2, because theta is the entire thing. If you see how they define theta, this is the entire theta. Yeah, you're right.
Thank you.
So this is theta by 2. Okay, so the last thing of this class before we go for discussion for different examples is stability of Weir wall. Means, imagine you had this wall, stream is moving and you put this wall so that water will move and it falls like this if you have opening. This wall has to be, there is always exerted pressure on it. So that pressure is basically static pressure that we discussed last class. So I just want to just write it here so that you know that this is part of the design. A lot of times it depends on what's the width of that Weir would be based on how much water you have. So as I said, as height of water increases, the pressure on the wall will increase because pressure depends on the height of water. So H rho G, that's what we pressure. This is the maximum pressure. So that pressure depends on height. Okay. So the height increases, you need to have enough structural support so that it doesn't break or fall down or topple. So that's why it's important to calculate what's the maximum pressure on that side. This is another reason a lot of times, for storm water, people create this kind of a barrier and to direct storm flow in certain directions. And so that depends on multiple factors, not just the pressure, but also the soil seepage rate, geotechnical property of soil. But for here, we're not going to go details about that. You just understand that this design take into account for the pressure exerted by the storm water. And so conceptually understand this one, so that pressure depends on water height, because the height basically tells how much weight of the water above that point. Pressure varies with the depth of water. On the top surface, there is no pressure because if you over here, there is no pressure because there is no water. As you go down, the more water on the above it, so that means pressure will increases. Also, pressure depends on wall inclinations. If you have this straight wall versus this wall, the pressure will be very different. In fact, it is more stable to have this kind of inclined wall. That's why you can see this big dam has this shape like this. Okay, they don't create a vertical wall, and just to avoid that pressure. So this is just an example. Vertical wall. What is the pressure? The force is 1/2 times h. H is the height of water. This h, and this is specific gravity. So that's rho g. This is density of water. Density times this is gravity, and this is height again. B is the width. Okay, so width of that wall over here. So for vertical wall, that's the pressure. All it's showing in the picture here, that in the very top surface, the pressure is very low or zero. As it goes down, it increases with depth. That means at this spot you have maximum pressure, and the force will be maximum. And that proportionality is is already written here. I am not going to ask example question on that. I'm not going to just know conceptually what that means. If you increase the depth, pressure will increase, and why it increase. So that's the concept, and I want to show that these are the example questions. These are the questions for your homework or last homework. It is very similar to the question we just discussed. Okay, and these are already questions are on the similar questions were in the handout. So you should read those handout so that you will be able to solve this question. This will not take more than one simple formula. You put the value, you get the answer. These are not difficult questions. These are more like a short questions, but we carry the same point because I just want you guys to try work on it. And we solve most of the example questions similar way, or if it is not, you have difficulty, then just check the handout. Handout has all these different type of questions. The last question, question 5, is based on bioinfiltration or biofiltrations. The concept, absorption, all that you already learned before, but how to apply and do it, you learn actually in the previous class, CEE159. You also learn if you take CEE164, you already know this question. So we'll learn this one in the next Tuesday. This is part of the midterm, so I just want you to make sure that if you don't know how to solve this question this weekend, don't worry, because we didn't cover it in this class yet. So this class will be covered on the 11th lectures, which is on Tuesday. But before that, all 4 questions you could solve. It's basically simple question like what we solve in the example today. So those homework, or the last homework, I also wanted to tell you that I uploaded the midterm questions. So what we could do is, this is the last year midterms, last year or 2019, I to check. Anyway, this is actually this is 2020. This is spring 2020. So that's the last year midterm questions. The reason I put it here is because what we can do is every day we can discuss one question here from midterms, as well as we have 3 classes including today before midterms, or 4 classes. So we have a couple of questions. This is one question. This is another question. This is another questions. Obviously, we can't discuss today this one because we didn't cover that. These 3 questions will cover in the next couple of lectures. So today, in the second half, we'll go through these questions because many of them you already learned it in this class. So I'm going to discuss this today. And the second half, we don't have to discuss all of them, but I can discuss any question you may have from homework number 3. We discussed that last class, but just in case anybody has question, we can discuss. Or we can discuss these questions or examples, including your project. So I would say that let's start taking the break for 10 minutes before we join. But any question before I stop recording?
Professor?
Yeah.
So which lecture does the midterm test up until? Is it week 6, lecture 2, or?
So basically these questions. Okay, this question we're supposed to cover by this week, but we didn't cover. So this is one of the question in the midterm. So I want to make sure that you have that.
So we'll be tested on contents up to lecture 11, up to and including lecture 11, and that's a cutoff.
Yeah, if we fill that one. If let's say some of the same content goes to spill over lecture 12, I will tell you exactly.
Okay, for sure. And
the
okay,
midterms is on lecture 14, right? So you still have one more week.
Okay. And also in one of the earlier slides, when you were talking about hydrostatic pressure on the wall, the F subscript R, does that just stand for like the force at a particular point in the wall?
Yes.
On the wall? Okay.
That
And
force,
also, sorry. Did I interrupt you?
No, I think I said wrong thing. It's not force on any particular point. It's a force on the wall. And the reason they put it there is because they are looking for the center of mass wherever it is, and they put that value there. So this is the total
So-
force on the wall.
Oh, so it's on the entirety of the wall.
Yes.
Okay, got it. And
Mm.
also, in one of the even earlier slides, there's like an example that I'm not sure if you skipped through. It's calculate flow when depth of water in the pipe is half D, 0.94 D, H equals D. It's after the effective radius slides. It's like 2 slides under the effective radius slide.
Okay, so this is effective radius. This one? Oh, no.
Yeah, this one.
Okay.
Did we cover this just now?
Yeah, we covered already this one. So it's just the only thing changing is this 4.5. As you see, this number is changing. Everything else is same.
Oh, okay, so it's just the same. It's the
Yeah.
same math.
Same
Okay.
math. Only thing that changes here, you just replace 4.5 with that, you get the number.
Okay, got it. Thanks.
Okay, good question. Any other question before I stop recording? All right, so when we come back, we'll discuss questions like we'll have a breakout room. So every room will give few questions to discuss among yourselves. So this will help you prepare for the midterms. And that way you have enough time to prepare. Okay, so I'll stop recording now.